Hi, and welcome to today's webinar. I'm Jasher, Application Engineer with CADVision Systems, and today we're going to have a look at sketch curves and continuity. Before I continue, I'd like to give credit to Robert Jost, as most of the data in this webinar based on his reference to his works. So today we're only going to cover three things, three simple but powerful topics: continuity, conics, and splines. Now, what is continuity? Basically, it's moving. Okay? From a 2D standpoint, it deals with geometry transitions from one type to another. Okay? For example, here. Okay? Now, splines, when it comes to smoothing of splines, is basically how smooth it is throughout its entire span. So, why is continuity important? Alright, now this is mostly when you design consumer products. Okay, so here, beauty is more than skin deep, right? So, what are the products that will be designed? What is the requirements? Okay, should it be nice to look at? Smooth finish? Should it be good to hold? Ergonomic? Okay. Are there a lot of let's just say the geometry is complex, the surfacing is complicated? Will there be a lot of smooth transitions between these features? Okay, so this is where continuity plays a role. Okay, not only does it make a model look good, it also makes it nice to hold. Now, continuity from a CAD standpoint can be looked at from three factors. Okay, direction vector, okay, radius of curvature, and the magnitude of the vector. Now, some of us have faced the following questions before. What is this C1, C2 surface standards contain? So here let's have a look at them. Now, the first group of definition will relate to the parametric continuity. Okay? If it's a C -1, it's discontinuous. The entities do not contact each other. If it's C0, there is contact, but that's just about it. There's no tangency involved, no magnitude constraint involved. If it's C1, first derivative continuity, there is a tangency constraint now. Then we can continue on to add a further constraint, and that will lead to a C2 surface. Second derivative continuity, okay, curvature continuous. Of course, we could go on C3, C4, etc. Of course, with C3 is basically now there is another constraint, the rate change of acceleration, but most CAD software only reach until the C2. Another group, or another way to define continuity is a geometric continuity. Okay, so G0 and G1 are basically the same as C0 and C1. However, SolidWorks uses the G2 continuity. Okay, so G2 refers to equal curvature. Okay, the radius of curvature is the same, but the magnitude can be different. It is less precise, okay, less precise compared to a C2, but it gives the user more control. Okay, so you can see here, the magnitude may be different for a G2. So in SolidWorks, constraints are added via relations, okay, sketch relations, coincident. Then you add a tangent, and finally you add an equal curvature. Of course, you can add an equal curvature straight away, or to add a tangent too. Okay. Then, of course, from the viewpoint of surfacing, okay, the constraints will be boundary, when you're using your lofting or your boundary, there's always the options to add tangent to the edges and so forth. Okay. Now, how do I check and ensure that my curvature or my spline or my curves are nicely built? There are several tools, for example, curvature combs, zebra stripes, curvature analysis, tangent edge phantom font, and applying a shiny appearance to model. We'll look at some of them. Alright, now let's have a look at how this what's this continuity all about. Okay, here in this example we have a C-1, no contact whatsoever. If I drag it across, okay, remember there's still no relation here. This is a C0, it's just contact. Okay, in fact, let's turn on the curvature comb. Okay, you can see that there's no contact here. Okay, now I'm going to apply a tangent. So you can see that while changes are made, the curvature comb gives me a reading that shows that the curves are pretty much, the normals are pretty much stabilized here. If I go one step further and add an equal curvature, you'll see that now the tangency is not just the tangency that's controlled. The curvature control actually makes the surface much smoother here. Okay. So this is G2 here. Alright, let's have a look at another example. Surface. Now this surface looks pretty okay, but how do I know? I can use the zebra stripe. Okay, I can configure a bit of edit some of the how the zebra stripes is displayed. Once I'm done, let's examine this. Now you can see here it's pretty much consistent, very smooth blending. Here, not exactly smooth blending, but we can see that it's like a mirror image, exact mirror image. And here we have something that's discontinuous. It's not very nice here. So why this? Basically, zebra stripes gives us an opportunity to see how the relations affect the surface. Okay, like here, it's just G0. Here we have a tangent, and here we have a curvature continuous, or rather, I should say, equal curvature. So that's the difference. So zebra stripes is the first tool. Another tool would be the ability to set surface curvature combs. Okay, surface curvature combs is a tool that allows me to inspect the surface. Okay, and I can adjust the mesh density, especially if my surface is a curve, not just based on this sketch, but based on other sketches too. Okay, or I can use a dynamic function where I just move my mouse over. I can just mouse over and see the details of the curvature on the surface. I can also run, let's say, tangent edges as phantom. So you can see that you can see a slight difference between these two. Like here, it's just C0, but here is a tangent, which is a C1. You can see it's discontinuous, is dashed and dotted, and of course, a tangent edge is also an equal curvature is also a tangent edge here. Alright. Now another method is to use appearance. So we're gonna just turn off the edges, and we're gonna apply an appearance to the model. Either this or maybe this will be a better choice. Okay, so when we pan and tilt the model around, we can see For curvature continuous, the transition is quite smooth. Same goes for the tangent. But for a contact point, by contact with no tangency, the details show up very starkly. So that's how these are some of the methods and tools that we can use to check the continuity of our surface. Alright. Next, let's have a look at conics. So conics cover a family of ellipses, parabolas, hyperbolas, and circles. Alright. Essentially, they're the intersection of a plane and a cone. Okay. The angle of the plane determines the curve. Like here, if the plane is parallel to the bottom of the cone, it's a circle. If it's an angle to the cone, it's an ellipse. And if it's an even steeper angle of this plane, and this plane intersects the bottom of the cone, this is a parabola. It will generate a parabola here, okay, along the edges here. See ellipse here, and edges here. Then, if the plane is directly normal to the bottom of the cone and intersects the cone itself, this will generate a hyperbola curve. Now, with conics, we use a rho factor, which is the total height of the cone divided by, or rather I should say, the total height of the curve, okay, from its apex to the bottom, divided by the total height of the cone, which is a/b. So the result can fall into a few three ranges. If the range is between 0 and 0.5, this will generate ellipses. If the range is exactly 0.5, it is a parabola. And if the range of rho is keyed to between 0.5 and 1, it will generate a hyperbola. Okay. So this is with the rho factor is the value used to control conics in SolidWorks. Okay. So how can we use them? Alright. Now, instead of using if we use an arc, it's kind of limited because it's just a radius. Okay. Sometimes with my one cone like one corner like this, okay, this is not possible with an arc. Okay. If we use a spline to do this, a spline is considerably more complicated, as we will see in the next section. So, I mean from a mathematical standpoint, because as you can see from a conic, the math is just essentially y squared to 4ax. Okay. It's a second order curve, so we don't really have to deal with the problem or the issue of reflections. Okay. And as you can see here, it accommodates a wide variety of shapes. Okay. You have so many options to make bridges between corners, and it is easily constrained to adjacent geometry. In fact, too easily, so much to the point that you can over-define it. Or I shouldn't say over-define, I should say it's more towards it's like if you constrain it too much, it will actually reduce its flexibility. So as we here we see that for conics currently, as of 2015, the ellipse or the conics are not supported in 3D sketches. And as I mentioned just now, because it's easily constrained to adjacent geometry, sometimes you might get carried away, and if you make a conic G2 or something, it drastically removes its degree of freedom. Okay, now let's see how we use conics in SolidWorks. So there we go. Alright, so I have this surface and I want to bridge this surface with a corner. So for convenience, I will generate an intersection curve. Okay. Oh, I selected it just now. Yeah. Alright. So having said that, I'm going to show you how to use the conic. So I can just click here and then click here. So I can now just place this conic. As you can see, when I move them, the row changes. Okay, and I can just click. So I can just adjust it. Oops. Okay, adjust it like this. You see a tangency is auto created because I think I cannot turn it on. Yeah, I turn on auto tangency. Of course, if I turn it off, I am free to place it however I like. Okay, you can see that if I follow this intersection, I can add the tangency, but if I don't want to, I'm free to go however I like to deal with it. See, so there's a difference between tangency, okay, between having tangency and no tangency. But generally speaking, we want to put tangency because it generates a nicer surface. Now, as I mentioned, one slight issue is that if I were to set this to say equal curvature, see, kind of fully constrained already. Sketch is fully defined. If I have to add a dimension to it, over constraints it. Of course, if I remove the curvature continuous, instead I can control the row, control the conic cone via row. Let's see. Okay. Now, if I were to create a freestanding conic here, for example, somewhere something like this, I have the option to actually make a symmetrical conic. Okay, here you can see that it's not symmetrical, but if I need symmetrical, I can just try move to the middle and SolidWorks will generate a intersection line for me to set the conic, symmetrical conic. Okay, so these are some of this is what a conic is all about. Okay. Now let's go to the third section, splines. Okay. Now in SolidWorks there are splines and style splines. Okay. Spline is like this. Style splines will use these handles to control them instead. Okay. So they are curves, but they are different from a mathematical aspect. Okay. So style splines are basically Bezier curves, if I'm not mistaken. Then splines are B-splines. Okay. So their purpose is to create continuous freeform shapes. Okay. So let's have a look at this. So next, for an arc, basically it's a radius. Okay, it's part of a circle. With a conic, okay, that can be part of it actually encompasses the arc actually. Okay, and for Bezier curve or the style spline, okay, we can have multiple degrees, but the span is usually one. It's one all the way. That's the difference between the Bezier curve and the B-spline or the normal spline as we know it. Okay, multiple degrees are supported, and multiple spans are also supported, as you can see here. So there's one segment here, another, total 4. So let's have a look at our style splines. Okay, so basically it's a control vertex and control polygon. Now I will show the model here instead, show how it's used here instead. Okay, so I can access splines through here. Spline and style spline. So style spline, if I'm not mistaken, was introduced in 2014. Okay, so to use it, I just click and generate the form of it. Okay, if I want to discontinue, I just press escape. So here we have 1, 2, 3, 4, 5. Okay, we have probably 5 degrees of freedom here. Oh, 5 plus 1, actually 6 actually. Okay, because 1, 2, 3, 4, 5, 6 points of control here. Alright, so to control it, I can just drag these points. Okay, even better, I can add sketch relations. Okay, and you guessed it, we can add dimensions too. Okay, and just like all sketch entities, we can choose to show the curvature combs to see how these splines are behaving. Right. So example here, let's just say I want to connect this from here to here. All I do is I just get my spline, in this case a style spline, and then I just click to generate my curve. So let me just make it nicer here. Okay, but as you can see here, the more control points I have, the more complicated my sketch is, or rather my spline will be. Now sometimes less is more. So suppose I want to remove some of these control points, all I do is I just select them, press delete. Okay. If I need to add them back in again, I just right click, select insert control vertex, and click on the places that I want to add these style splines to. See? Okay. Of course, let's just say for this example, I just want to make it curvature continuous here, and I'll just do some of these additionals here. And just form my curve. Okay. So in this case, I'll just let's have a look at. I can just add my, or I can just activate the curvature comb again to see how it behaves. Okay, and of course adjust accordingly. All right. So this is how I can use style splines. Okay. So for the V spline, as we see here, basically we add the points to create the spline. We can also use control vertices or control polygons and spline handles to control how our spline behaves. Okay. So here I'm going to create a spline. Okay, here I just click the points. Okay. And once I'm done, I just press escape. So I can just drag them around like this. As you can see, as you notice, that there are handles here. Now the handles don't show until you activate them. Okay. And these handles they support relations as well as dimensions. Like here, I would like to dimension this handle so that it is at an angle. So I select this guy and this one, and there we have it. See that I've added dimensions here. Okay. So as usual, we can show our curvature comb. We can show minimum radius. Okay. Minimum radius, which changes depending on how the spline changes. Okay. So you can see there's quite a difference between how we control splines and V's and style splines. Now, if I want more control, I can add a control polygon. So what it does is that I can just drag this guy around. Okay. I can also drag the points around. So, of course, if I want to add additional points, I just right click and then select either insert spline point here. So I can just insert how many I like, however many I like here. Okay. If I don't want it, I just click on it and I delete it, just like how we deal with the control points here. So these are the controls for spline and B-spline. Now take note that you cannot add dimensions to the control polygon, the spline polygon here. Okay, so that's one notable difference between the control polygons here and the spline control vertices here. Okay, you can only dimension the points in splines, not the control polygon in spline. Okay, so this one is now a little background about splines. So as it is a B spline, okay, as opposed to a style spline, as mentioned just now, a spline is made up of can be made up of several spans. So in this case, this spline here has 1, 2, let's see, yeah, 1, 2, 3. Okay, here's 1, 2, 3, 4 points here. Okay, so there are actually 4 spans here. 1, 2, 3 spans. Sorry, 3 spans here. So the first span is created using the following function. Okay, this red line, which actually extends under here too, and then SolidWorks will generate for the second span the blue colored line. Here is overlapped by green. Okay, there's always an overlap here, and for the third span, it overlaps this green here. Okay, so having said that, you can see that actually these are where the control vertices are aligned with. Okay, by controlling these vertices, we're controlling these invisible functions here, which in turn control the visible spline itself. So the next question is, which is better, style spline or our B-spline? Okay, the thing is, the issue is not which is better, but the issue is which is more suitable for what job. Okay, for style splines, generally speaking, there's a higher level of internal continuity because there's only one span, so it's easy to control in some cases. Whereas for a B-spline, you can create a wider variety of shapes faster, because as you know, you can just quickly add those control vertices, and they can change its curvature more abruptly. Okay, I can see here, and just kind of change its curvature so quickly, so dynamically. Okay, see, very fast I can make changes to it. Okay, so in summary, continuity is important for smooth geometry. So, and then conics are robust curves with very good continuity. Robust in the sense that they lend themselves well to creating a variety of shapes, whether it's just your plain old circle, or your ellipse, or parabola, or hyperbolic curve. And it's not just limited to symmetrical. You can create asymmetrical ones. Then the style spline maintains the highest level of internal continuity, whereas the B-spline can create complex shapes quickly, which as you can see here, kind of a compromised continuity here. Okay. So having said that, we've come to the end of today's webinar. Okay. I would like to thank you for attending this event. Okay, I'm Jasher, signing out.